Sorry for the mishap. My name is Umar.
My name is Santo, and we're from JP.
Today we're going to be presenting about computer vision depth sensor power smart cable for real-time object detection and navigation assistance for the visually impaired.
So let's first talk about the motivation and problem behind this research. Right now, 2.2 billion people in the world have some form of visual impairment. Now, out of these 2.2 billion people, around 36 million people are blind. Now, conventional caves and ultrasonic ETAs can't identify what the obstacle is, but can give some indication to where the object is in relation to the user. This means that there's some need for semantic awareness, depth estimation, and low-cost real-time performance in one singular smart cave. Now let's talk about our research objectives. We wanted to develop an affordable, real-time assistive cave that integrated the following features and components. We want to have a transformer-based computer vision model for the task of object identification. We want to use a Raspberry Pi, a stereo depth sensing sensor that gave the RGB depth values, the multimodal feedback in the form of audio and haptic feedback for a PCB, and from all of these components combined, we want to categorize these obstacles, estimate their distance, and provide the user with low latency alerts. Let's also talk about the background and prior work in this area. Currently, the YOLO V3 Tiny and Mobile Net SSD models have been deployed on smart caves. Now, the issue with these models is that they have high false positives, and they perform very poorly in crowded or low-light settings, which means that these models are not applicable to real-world scenarios. That means that there's a need for transformer-based detection for real-time inference on these edge devices.
Now what we've seen from our parts, let's look at our system architecture and see how they all work together. We have four main components. First, being the first image you see up there, or the Intel RealSense D435i RGB depth camera. That is inputted into our Raspberry Pi 4, as well as being powered by our LiPo battery. On the right of my left, you guys can see the PCB, our custom-made PCB, which is taking those inputs and directly giving feedback to the user. Lastly, this operates fully offline, requiring no Wi-Fi or cloud dependency. So more on our hardware, the first image you see is the computer-aided design or CAD of our model for our build. The camera is mounted towards this on the screen at a 10-degree tilt using a custom 3D printed ABS motor, and it's powered via that 10,000 milliamp hour battery showed. It has 5 hours of continuous playback, and the PCB as well. It simplifies wiring and manages haptic/audio outputs. So a little bit more on the PCB. You can there's many components, but two I want to really highlight are that ESP32 and the haptic sensor. So the ESP32 takes an input from Raspberry Pi, there's something called URT or stereo, and that is basically giving input as well to the haptic feedback to feedback the user and guide them.
Now let's talk about object detection pipeline. We use the detection transformer and then train via NM detection. NM detection is an open source custom object detection toolbox, and this is based on PyTorch. Now we take this detection transformer and we fine-tune it on the COCO dataset, on the subset of the COCO dataset. We specifically fine-tune it on the classes of people, vehicles, bicycles, benches, and traffic lights, as these are the ones that are most related to mobility-related tasks. And then we deploy it using OpenVINO for ARM acceleration, so the latency would be decreased. And then, as you can see here, this is the detection transformer pipeline. And what's great about this pipeline, it's an end-to-end transformer architecture.
Next up, let's discuss a little bit about our depth estimation and feedback through our camera. The depth is processed through something called RealSense SDK, and it's using camera intrinsics. We also use Gaussian smoothing for noise reduction, and we have some feedback tiers, including 0.5 meters showing more danger and having strong vibration and high audio. We also have the 0.5 to 1.5 meter mark, signifying medium feedback and directional audio, and then we have the least dangerous aspect, the 1.5 meters, being muted unless an object is approaching. We also have in the app visuals signifying feedback across the room. So now more on a little bit of camera intrinsics, and I'm not going to bore you with so many details because I know you guys are hungry. So I'll tell you a brief bit about this. We have two main ones, which would be the focal equations that go into our width and height. Those widths and heights come from the bounding box created with our depth transformer, and that is multiplied by the average height coming from the actual Intel RealSense camera in terms of speed, giving depth for different objects and to get the correct location.
Now, we also create a mobile app, so this smart key could be easily usable for anyone with visual impairments. So we made a Swift-based iOS app that displays the battery-level object detection logs and real-time feedback visualization. Now let's talk about the quantitative results. So as you can see, our detection transformer outperformed the YOLO baseline model for the mean average position and the F1 score. However, the inference latency, feedback latency, and power usage for the baseline model was in fact lower due to the fact that the baseline model has a simple architecture. Now, we also decided we would take a smart key and test in the real world. We tested in 4 different environments versus 2 different tasks. For if it's able to accurately detect the objects, and if it gave the correct feedback response rate based on detection of those objects. And as you can see, the average was around 80 to 90%, which means that this model performed very well in the real world.
Now that we've seen some of these quantitative results, let's talk about what they actually mean. So we've seen that the transformer-based detection enhances contextual understanding. We also saw that depth and vision synergies allow prioritization of moving obstacles. We saw that fully edge-based operations ensure reliability and privacy for our users. We saw some limitations, including the low light performance and higher inference latency than YOLO V5, but as shown in our image here, we saw that the depth transformer more accurately performs these object estimations compared to our competitors such as YOLO and faster RCMS. Now, in terms of our future work, we hope to address that low light problem by upgrading our RGB input for low light and gray conditions. We hope to integrate infrared sensing for navigation and ultrasonic sensors for redundancy. We hope to enable smartphone pairing for auditory navigation cues and logging of navigation data. And we plan to use long-term user data to improve AI model adaptability and real-world accuracy.
We'd like to thank JNL for funding its women's research, and you can contact us at these meetings.
Thank you so much.